ম্যাম স্টার্ট করুন ম্যাম।
Good morning, everyone. We are live now, and I like to extend my warm greetings to all participants who are present in our webinar. I'd like to welcome specially Dr. Purnananda Nandi, our respected speaker from BART, to the webinar on Science and Technology of Glass, organized by the Department of Physics, SREEGOPAL BANERJEE College. All of us, we know that glass is a structurally disordered material. It is prepared by first quenching a material from the liquid state to the solid state so that atoms cannot rearrange themselves in the crystalline form. The microscopic structure of glass is comparable to that of a liquid in which the individual constituents form an irregular network without a long-range order. In general, glass is hard and brittle substance that is usually transparent and translucent. It may be comprised of a fusion of sand, soda lime, and other materials. In order to eliminate this inherent brittleness, it must be thoroughly processed according to optimal strengthening or tempering protocols. Now, glass is transparent in the visible range of electromagnetic spectrum, and it has high resistance to high temperature and chemicals also. It is also not affected by the atmosphere, and it is an excellent electrical insulator. Because of these properties, glass is used in various domestic appliances, in laboratories, in optical fibers, etc. Properties of glasses can be suitably altered by changing basic ingredients and adding a few more. In this webinar, some special uses of glass in different fields will be discussed. The webinar will be moderated by our convener, Dr. Biplab Goswami. Now our chief patron and teacher in charge of our college, Professor Debashis Rai Choudhury, will deliver formal welcome address and will announce formal commencement of the proceeding of the webinar. Once again, I like to say that for me it is a great honor to welcome you all. Hope you will enjoy the webinar. Over to Debashis sir. Debashis sir.
Okay. My dear colleague, students and research scholars, the Department of Physics, SREEGOPAL BANERJEE College has organized a webinar on science and technology of glass. In this pandemic situation, when regular academic activities are not possible, the internet is the only option. We don't know when the normal situation will be back. But I believe in normal situation also, this online academic activity will be an alternative to the regular ones because it is becoming very much popular among the scholars and all and among the scholars and everybody. One definite advantage is that it is cost effective, and moreover we can listen to any scholar or from any part of the world. That is a great advantage of this webinar. About the topic, I am not qualified to say anything because I am not a student of physics. My subject is political science. So I heartily welcome our guest, Dr. Purnananda Nandi. I am grateful to him as he has reserved some of his precious time for our college. I wish every success of this webinar. Now the webinar may be started. Thank you very much. Over to Biplab.
It's my pleasure to introduce Dr. Purnananda Nandi, our speaker in this seminar. Dr. Nandi did his BSc and MSc from Visva-Bharati University, Shantiniketan, and did his PhD from IIT Guwahati. After that, he joined the Center for Photonics and Photonic Material, University of Bath, UK, as postdoctoral fellow. Coming back to India, He has served Raja Ramanna Center for Advanced Technology, Indore, as visiting scientist for the period 2009-2010. Now, he is the scientific officer at Bhabha Atomic Research Center, Mumbai, since 2010. With this brief introduction, I request Dr. Nondi to deliver his speech. Over to Dr. Nondi.
Thank you, Biplav, and very good morning to everybody. And I say thank you to Rima Madam also. He has given a very good introduction of the glass material. I think some of the terms she has told, I'm going to cover that also. And thank you, Devasi sir, also for giving me this opportunity to present. And thank you, Biplav. And my dear these students of the SB college. So I'm going to share the presentation now. Yeah. Excuse me, can you see the presentation?
Yes, sir. Slide is visible. You can carry on, sir.
Okay. So first, this is the topic of my lecture is the science and technology of glass, and I'm going to talk about some of the technological aspects of glass, because glass is a very common material. We have seen it in and around our houses very often, but it is also very useful for some high-end technologies like nuclear industries, optical technologies, and all. So I will talk about both the technology and the scientific approach of this glass. My lecture will be divided into three main parts. First, I will talk about introduction to glass. Then I will talk something about the applications of glass, especially for the nuclear field, and then some characterization techniques also, where I will speak about the testing facilities we have and how we test the glass when we make them. And this is a bit of a history. This slide. It is said that long ago, somewhere in the sands of Mediterranean seas, someone has a big fire, and is actually written in some of the textbook. And this fire has somehow melted the silica in the beach, along with the sodium in the seawater, and also some of the sea cells, which is acting as a flask for making the glass. So next morning, some people found there is some kind of new material. There are a lot of things happened accidentally in this in science. We know that the apple falling from the tree, and someone has invented the gravitational law. So glass basically made from sand, and as you can see, I am trying to show my cursor. Please try to follow the cursor. The sand is the main ingredients for making the glass, and obviously there are other materials like soda lime silicate glass. There are soda and lime and sand. When they're mixed and they are put into fire, then they will melt. And this, in the right hand side, you will see artifact is preserved in a kind of some kind of museum, where it is called the Roman glass, where the Roman emperors used to have the access to this kind of glass. So it's very old material. So nobody never knows who is the actually inventor of the glass, but Romans actually started using it in their different purposes in their houses. So this is a Roman glass and is quite old. Now, glass in India also came with the migration with some of the people and kings. And this in the left, we can see that there is a this is called the Sheesh Mahal in Agra, where you can see the glass has been used as a building material. And then at the right hand side, we have this bangles are made in a place called Firozabad, very near to Agra, where still in India they are making this glass bangles. And this is how it was made for generations they are making it. So glass in India is also quite old. Now, in the modern glass in India, I'm going to talk about some of the companies and research organizations here. At the very beginning, I want to talk about in the left, you can see at the top left, this is CGCRI, Central Glass and Ceramic Research Institute, which is in Kolkata. And this is quite old. It was started by, I think, 1960s. And it is a very renowned place for R&D, research and development of glasses here in Kolkata there. And then there are some other professional companies like Borosil, Saint Gobain, Asai Glass, then this Hindustan National Glasses, Gujarat Guardian Limited. These are the few companies which are commercially making glasses in India and in various forms and shapes and sizes. So I will move on to the next slide. This is the float glass. So I told you that slowly I'll go to some kind of scientific discussion, but still, in the beginning I will try to make it more simple and the application based and its properties. So this is a float glass. It's a huge technology. It's not easy to. It looks very simple, but it is a huge technology. The main characteristic of this glass is this is transparent, and for that you need a very good polishing quality in both sides of the glass, and that is how you can make only by floating the molten glass on top of a tin. So there is a lot of technology there, and that's how the people are making the float glass. And the main advantage of this is transparency, and we will discuss some of the techniques of measuring the transparency and how we can use it for other purposes and scientific analysis. Next is the glass. Mostly we call this metal glass also sometimes we call glass, but it is technically wrong, but anyway we will say it here. So glass, we use it in the to have a cup of hot tea also. The main thing what I'm trying to do is low thermal conductivity of the glass. So basically, even if you are holding a glass, as you see, this is a glass blower trying to melt the glass or join two glasses using a glass blowing torch. And so what they are doing, they are trying to put it in a very high temperature. This is around 1000 degrees Celsius temperature. And at that temperature, the glass will be soft, and then they can change the shape of, and they can join these two glasses. And the main problem is, even if they are molten, the technician can hold the glass very near to the fire because of the low thermal conductivity. Now this is the Corning Gorilla Glass. You can see a small gorilla looking at the mobile, and this is another. This is made by Corning Gorilla Glass. Its main technology of this is the hard to break and scratch glass. As you can see, Corning is a very big industry in US. Is only the glass-based industry and a very big industry. And they are doing a lot of R&D on glasses. As you see, this Gorilla Glass which is only 0.7 mm thickness, and have a very hard to break. As you can see, you can bend it to so deep, like 70 mm depth it has been bent, and still it's not breaking. And it's also very difficult to scratch also. So that's how we can change the properties of the glass. So main property here is hardness. I will talk about hardness also at the later part of this lecture, where we can measure the hardness of a glass and this thing. So hardness of the glass is also important. And then tempered glass for safety. The glass has been used in very every field, almost in our daily lives, and you can see the automobile industry is using the glass, and they are using this glass as a window. Now the problem is that they are using tempered glass for safety. Why I'm telling you, if you look at the picture in the right hand side, see, this is the fragments of a float glass. This is actually a float glass, then they have been tempered because of thermal stress given into that. So the difference is the way it is breaking. If you see that in the right extreme right, the fragments of a float glass, if there is an accident in the car and someone is trying to come out of this that car with a broken glass piece like this, then obviously they are going to get hurt. So now, because of the tempering technology, what will happen, that the glass will break in very small pieces, and that's then it will be much easier to get hurt with this kind of accidents. And so it is really very useful for the safety purpose. And then I will talk about this kitchen glasses, which also again have low thermal expansion. It's very important. Low thermal expansion is important. I also talk about how to measure the thermal expansion and these things. And Borosil is one of the companies making in India. This is microwave safe, as you can see, microwave safe. And that's main thing is even if you heat it at up to certain temperature, like if you are having some rice and you are heating it up, then the glass is not going to break because of thermal mismatch or thermal stress. And also in the left, you have this prestige cooker, where they are using the induction type cooking, and there also we need a glass top especially for this kind of application, low thermal expansion. And I'm slowly moving on to the more scientific approach of the glasses now, more specific applications. And one of these things is optical instruments. As you see, every single lab in science, you'll see this kind of microscope, which is very important to see the microstructure of the material, or whatever material is a physical, chemical, or some kind of biological material. You have to see it through the microscope first. And for that, we need a lot of lenses and this kind of things in various shapes and sizes. As you can see here, it's a huge industry. The cutting and polishing of the glass, the angle cutting of this thing is to make the prisms and all. It's a very precise technology, and a lot of work has been done and is still going on. And you see that DSLR camera in the right, which is also using the glass as a main thing for focusing and defocusing and this kind of applications. So many lenses and prisms and different type of filters are made out of this glass. Now I am little bit moving into a slight different application. It's more very specific application of laser. We know, everyone knows what is a laser. It's a light amplification by stimulated emission of radiation. But this is one of the very commercially available lasers, very low cost commercially available lasers there. And you can see there are different components here. It's very difficult to understand from this picture, so that's why I've given a diagram for this. So please look at the diagram here. The three main components are there for the laser, to make a laser, and that is a pump source, which is the flash lamp, and then you have a crystal, which is the laser medium, and sometimes we can use the glass also as the laser medium, and the optical resonator. This is the main three things to make a laser work. So for the optical resonator, we have a highly reflective mirror at one side and the partially reflective mirror on the other side. And the pump source is also a flash lamp. And you can see here the flash lamp is going round and round around the crystal here, which is a pink color. But the crystals have some kind of problem. I'll go to the next slide. See, this is the woman scientist with holding his glasses. The glass has the advantage of making a very different shapes and size. As you can see, crystals we cannot make it in such big dimensions. And these are the crystals. These are the glasses actually made in very different shapes and size, and for very high powered laser applications. And in the left, I can another just a point of this thing for the students. There is a difference between the incandescent light and the laser light, and as you can see, the laser is all red light coming, whereas a incandescent light, it is having all the colors like red, green, blue, yellow, and so it is incoherent light, and the laser light is a coherent light, and it's monochromatic, and it's unidirectional, and that is because the stimulated emission. I'll come back to this stimulated radiation again at some point later. But this is the very basic difference between a coherent light and incoherent light. And laser is a huge in the research and development, and also for technological application. Laser is a very huge thing, and at the base of you can have a glass which can tune the quality of the laser and the wavelength of the laser and things like that. Now, another very big application of glass is internet glass, as madam told in the beginning, that at the very heart of the internet is this optical fiber. Now, I'm going to talk. This is a fiber to home. This thing is available in Mumbai, and you see the directly fiber coming into the house. Now, how it is working is more important. See, this is a optical fiber. It's shown very crude way, but I will show you the fiber later on. And at the design of the fiber is, you see, there is a blue color core in the middle, and there is a cladding outside. Both are glass. And it's amazing the technology, that how they can make the two different refractive index inside the glass. And the reason for making the refractive index variation is to make the light go total internal reflection inside the fiber, so there is no loss. When there is total internal reflection of the light inside the glass, the light will only propagate inside the glass without any loss. The light is not coming from this medium to this medium. So that's the beauty of it. So, and the reason why the optical fiber is more used compared to the electronic cables is because the optical fibers is having low loss. So everyone needs a repeater, this amplifier. So, but for optical fibers, the repetition is very low. So I think for optical fiber without repetition, you can go up to 100 kilometers, whereas for this electrical cables, you can go only up to maybe 1 kilometer. So how it works is we have electrical signal, and then electrical signal will be converted into light using this transmitter, and this the light will be launched inside the core, and then they will go bounce back and forth through this optical fiber, and then can get to the detector or the receiver, and then again convert into optical signal output. Next slide. So this is how it's working in the total internal reflection inside the fiber. So if you see the first picture here in the top left, If you launch the light like this in a slight varying angle, at one point you will see the light is coming back to the fiber, to this medium. This is one medium, this is another medium, and this is how the fiber is made. And see, this is in the right hand side, you see someone is holding a fiber, and the light is leaking out of this fiber because of the bending of the fiber. There is a lot of loss in this point. If you bend the fiber to some point, then the light will leak out. But if you keep it straight, then the leaking of light is very low. But that's how it is launched. So launching the light into the fiber core is also very important. That's what is shown here. So the light is almost very, almost 1 mm or 5 mm thick light, pencil light is coming. Then again, you have to use a lens to focus the light, and that angle will be decided by the focal length of the lens and all. So that is how we can launch the light at a particular angle so that the light stays inside the core and go back to the whatever direction it is going to there. So this is core cladding, and this is how glass has been used to transmit the data, and it's the backbone of this optical fiber network, internet. Now this is also another technological brilliance of the glass to metal seal. See, this is a bulb. As you can see, this is actually a bulb. It's a halogen bulb, and there is a metal string here. So when you put some current, and then what will happen? This wire will glow, and it will produce light. But when you do it in outside, in a normal atmosphere, what will happen? They will oxidize because of the temperature. And when it oxidizes, then very quickly it will be, the circuit will be broken and will not be able to produce any more light because the current will not flow. Now there the glass is coming. What will happen? The glass is non-porous, so glass will not allow any gas getting inside. So if you can seal the metal inside the glass, and then you evacuate the glass and the metal and then seal it at the bottom, what will happen then? The metal inside this tube will not be oxidized. That's why it will act like a light source for a very long time. It's an awesome light source. Is mostly used in the spectrometers. And see, these are the electrical feed through which the electricity will be launched inside this thing. And the main important part for this is the thermal expansion of the glass should match with that of the metal. That is very important. So that is what it is shown in this diagram here. Here delta L by L has been plotted against temperature. So even if you increase the temperature of the glass or the metal, they should produce some kind of this straight line at certain temperature, at least up to the working temperature, where the glass would be sealed. At the room temperature, glass will not seal with the metal. You have to put it in a certain temperature, and that temperature that will seal with this metal, and it will be just evacuated, and then there will be no gas leakage inside. So that's how it is. The glass to metal seal is working. Now this is a machinable glass ceramic also. As someone everybody knows that glass is a very fragile material, right? If you drop it, it will break, because what happens at certain energy you put it in the glass, the cracks propagate very fast inside the glass and it will break off everything. Now, if you can stop the propagation of the crack, then the glass will not be fragile anymore. So that's how these machinable glass ceramics are made. It's a commercially called MACOR. It's a huge in the aeronautical engineering and all this stuff. They're using it in a very large scale. And this is what it is happening. You can make screws and these things out of it, and it's glass. So it is really a magic. And if you see the microstructure, this is the ACM picture of the MACOR. If you see the microstructure, you see this mica-like thin layers are observed, which is actually resisting, is arresting that propagation of the crack. That's why this glass is not fragile, but obviously it has some certain limit, but it has not as fragile as glass, normal glass. Now, this was one part of this. Almost I can say that I have completed the introduction part, and this is a little deviation from glass at the beginning. Then I will go, because I am from BRC, so people have some kind of expectation. I think everyone should know also this is little bit deviation that I'm going to go from glass to nuclear power. How nuclear power is generated is very, very important in BRC. And this is the clean energy. As we see, this is only clean energy, but it is also very dangerous. As people can see, there are a lot of accidents happened in other part of the of this world. But how it is working, I will say, is at the basic of this thing is steam. As you can see, this is the building. There is a containment building where the reactor is there, and where the nuclear materials are being handled here, and that will produce some kind of heat, and that heat will be transmitted through this closed channel to the steam generation, where there will be water, and the steam will be generated and will be streamlined through this, and to another chamber where the generator will be, there will be a turbine, and from there you will go to the generator. So that's how nuclear energy, nuclear power plant works. It's very similar to the thermal power plants, but only thing is this difference. Thermal power plant directly burn up the coal and you get the steam generated. But here we have a reactor, so we are using some kind of nuclear reactions here that I will come back to there, and that is how energy, the thermal energy is generated instead of coal, where you produce a lot of carbon dioxide. So that's why it is clean energy. And this is the three main components of a nuclear reactor. This is, first we have a nuclear fuel which will generate that heat, and then there will be a moderator, and then there are controllers. So all material science, you see there are a lot of material involved in this process, and I'll go more elaborate now. This is the nuclear fuel. This is uranium oxide. Why it is nuclear fuel? See how the energy is generated is using uranium. Uranium 235 is a natural ore. Uranium 235 oxide, uranium oxide is a natural ore. When you expose it to a neutron, a certain neutron with certain energy, if you are exposed to a neutron, what will happen? It will combine with this neutron and will become an unstable nucleus, uranium 236. Now, what will happen after some time? This will break up with a barium and a krypton, and that will produce another 3 more neutrons. Okay, and with access to that, we have a lot of energy coming out of this nuclear reaction, and this is what is called a fission reaction. Okay, and now, but this is not sufficient. When you need to do it more and more, that's what is called chain reaction. So when we have these 3 more neutrons, they are going to activate another 3 uranium 235, and then they will again produce 3 carrier, and it goes on like it's what is called chain reaction, and it produces a lot of energy. But you need to transfer that energy, that heat, from uranium to the other part of this thing, so to generate the steam. So what will happen? We use the water as the coolant. So this uranium fuels and this thing will be dipped inside the water, and what will happen? Water will be circulated using a pump. So water will get the heat from this reaction, and that will transmit and this energy from this reactor to the other part. So, and as you see, this is how the chain reaction is working. So uranium 235 and 1 neutron was there, and it has been exposed, and it is getting to the other uranium 235, and it's producing 3 more neutron, and then again that goes to some other uranium-235 and gives this chain reaction going on. And but again, this is again very dangerous. You cannot keep it like forever. So at one point it will blast. Okay, you need to control that reaction. So sometimes when the heat is very high, so up to 300 degrees Celsius, they can hold this temperature. Beyond that, we have to observe the temperature of that nuclear reactor. If the temperature goes beyond 300, then there will be meltdown. So what will happen? They are all potential bombs, but there are techniques how to control. This is where the nuclear reaction control rods are coming. This is cadmium and boron. These are the material which absorbs neutron. So what will happen? See, there are two these fuel rods are A and D. Now the 2 is water. Now what happens when the 3 comes, this boron comes, what will happen? That will absorb the neutron from the which is making the chain reaction. Okay, so you put it in between and you can completely stop the nuclear reaction. So that's how we control. This is what is called control rods. So you can control the nuclear reaction in a very short time. Within 5 minutes you can control the chain reaction, so you can stop it. But obviously it is a potential danger there. And now what will happen now, this is where the glass is also coming, nuclear industries. So slowly I'm going to the application of the glass again in the nuclear industry. This is the biggest one, which is the radioactive waste management. What will happen? These nuclear reactors, they will exhaust at certain time. Every uranium-235 will be exhausted, and then they has to be thrown away. But we cannot throw it away because they are all radioactive, and we have to throw it in a very proper manner, that no human contact comes to that radioactive material. So what they will do, they will put in a liquid waste tank where there are a lot of acids will be there. They will dissolve them, and then they will evaporate the water. Then they will become like a solid powder. All these things, uranium oxide and all the disintegrated parts, will be formed into powder, and then again they will be mixed with the glass forming additives, and they will prepare a batch. Then batch will be melted, and they will be formed glass, and this glass will be again transferred into very deep geological positions where there is very minimum possibility that there will be some kind of exposure to the humans using those radioactive waste. So glass is the radioactive waste management. And then radiation shielding is also very important. See, when you are working in a radiation zone, there are a lot of alpha, beta, gamma rays coming out. Now, a simple tissue paper can stop the alpha particles. And this is the slide what's showing this aluminum sheet. A simple small 5 mm aluminum sheet will block the beta particles. But gamma is very high energy, and it can cross anything. See, it goes through tissues anyway, and it goes through the aluminum this thing path, and then even it can go over the concrete walls, and they can be stopped only by the lead. The lead shielding is very important. So lead is the shielding material. And then again, this radiation shielding window glass, where what happened when some point, this is the radiation shielding window. We're looking through, the people, their operators are looking through this glass sometimes, not always, sometimes they're looking through this glass for this automatic arms to do some kind of regular maintenance work. So that time they have to look through the glass for this thing. But again, there is a possibility of radiation coming from there. So we need a glass which is having radiation shielding property. So this is what is called lead glass, which is lead equivalent glass. If the thickness is very high, this is almost 10 mm, 10 centimeter, 20 centimeter thickness is there. But this is how radiation shielding window glass is made, and it's a huge, and this is very costly stuff. People in BRC also trying to do that. The final this thing is the glass microsphere, which is commercially called teraspheres, and this is again related to the radiation. See what happened, you can make the glass powder into as microspheres. As you see, ACM picture here. In the left, this is the ACM picture of the glass microsphere. So what this is in comparison is a hair. This is a human hair in the left, and compared to that, this is what we have in the is the glass microsphere, which is 20 to 30 micron diameter. And what will they will do? They can be activated using a neutron bombardment. So generally in the oxide glass, yttrium oxide, yttrium 89 oxide is there. You can incorporate in the glass, and then what will happen that you make the microspheres out of that, and then you activate it using a neutron source. So it will yttrium, as please look at the picture here, yttrium 89 will be converted to yttrium 90, and that will give the beta decay, and the half-life is almost 64 hours. So if you put this, if you can put this yttrium 90 inside the body, that can go it can be used as a targeted radiation inside the liver, and they are treated as a liver cancer and all. So this is also another useful application of the glass microsphere, and it's basically it's made up of glass, so it's not very harmful to the body, human body. Now this is the last part of this thing, and I will say this is the final part. We are moving into the glass making basic steps, and I will talk about some of the characterizing techniques. First, I will talk about how to make glass as a regular job for us. We see it very well. We have this big furnace that goes up to 1600 degrees Celsius temperature. So the three basic processes, there are a lot of complications in there. I'm not going to go there, but three basic steps is there. You make this is the batch mixing of oxides. They're like silica, sodium oxide, potassium oxide, calcium oxide. You mix them, and then you put it in the furnace, and then you melt it for 2-4 hours, and then when it's melted, it will be like this, as you see in the right hand side. This is what is called melt quenching technique. From the furnace, we have to take this out. This is the molten glass inside a crucible. So this will be like a honey. If you have seen the honey, how it is, but it is very hot. I'm telling you, this is looking at the color of the glass. You can see this is very red hot, and it's almost temperatures beyond 1000 degrees Celsius. And if you pour it, it's like a liquid. It will get a shape of this shape, and then slowly it will be cooled down, and then you have to annihilate so that there will be no thermal stress. To remove the thermal stress, you have to do the annihilate. These are the three basic steps. Now I'll talk a little bit about the batch preparation. Suppose we have a float glass which is having the composition like 15% sodium oxide, 10% calcium oxide, 75% silica. So, and in the lead glasses, typically it's a 10% potassium oxide, 50% lead oxide, and 40% silica oxide. So the process is the process for the batch preparation. You have to get all this oxide in appropriate quantities, and then you have to put it in this jar. This is and then you have to put some balls here accordingly, and then we put it in this planetary ball mill. This is called which is where these oxides will mix very well. It's very important to improve the quality, the transparency, the hardness, this thing, stray lines, thermal stress, everything will be related to this mixing. So it's very important part. And then this whole this powder, mixed powder, will be kept in this crucible. These are two general crucibles I have shown here. One is platinum crucible in the middle. This is a platinum crucible which is almost it's very costly, depending upon the weight. Is almost this one almost 10 lakhs is the cost. Whereas if you have an aluminum crucible, 99.7%, which is also not very reactive with the, if this aluminum is not very reactive with the glass composition, then you can use it as a melting crucible, and it's not that costly, but still 1,000 rupees maybe per crucible. So now I'm coming to the very definition of the glass. This is slowly getting more technical. So this is, remember this definition: glass is an amorphous solid having glass transition temperature. So amorphous, glass is amorphous, but not all amorphous is glass. Remember, this is amorphous solid, and also is having glass transition temperature. I will individually come to this amorphous and the glass transition temperature. Is, as you see a picture down there, this is the crystalline and the amorphous structure is given. Don't think it is a microsphere. This is just the atoms, circular atoms you think. So basically in the crystals, what will happen? We have the periodic atomic structure. As you see, there's periodic atomic structure, whereas in the amorphous, we don't have this periodicity of the structure of this atom. That is how is glass is all about. But again, it's very difficult to understand. If you have a crystal and a glass, it's very difficult to understand which one is which. So the technique for knowing what is if it is a crystalline or a amorphous is the X-ray diffraction. This is the very basic, very old, very basic technique where you have this. As you see, this is a Bragg law, where you have this incident X-rays and you have the diffracted X-rays, and you get a spectrum. This is we get this this intensity curve for this silica here, and this is very this pattern is very much this chemical specific, the crystalline structure specific. So if you have a very specific structure, we will get the very specific this thing. So it's a molecular fingerprint. So you know what kind of material is. Identification is also important for this this technique. Now, what will happen when we put the glass in an X-ray diffraction? What will happen? We'll see the same kind of this pattern pattern has disappeared actually, and it has shown a broad hump in this X-ray pattern. This is again this broad hump. I will say how it is coming. If you see the picture on the right hand side, this is the crystalline and amorphous, the same picture. Now, if you see there are two yellow lines here I have shown, these are the mean average position of the atoms in this line, and this is the another line. So you see, you can define these two lines. The average line of these two is very defined. That's why we have a very fine line. So we have a very fine refined this thing, X-ray diffraction pattern in this very sharp peak. But in the amorphous, we have diffuse peak because the average position is very diffused. We don't, if you see that this is a more broad average line for these two lines of atoms. That's why we get a diffused spectrum. That's what is the amorphous nature of the glass. Moving on, again, the long range and short range order, which is very often is associated with the glass structure. You see, I'm going to talk about this long. This is a 2D picture. I'll go to the 3D picture also a little bit. But obviously, the crystalline structure of the sand, if you see in the very left, this one, look at this picture. If you see this is the long range. All the atoms are having periodic atomic structure in the long range also. In any direction you go, they have a particular pattern. But when it goes to the quartz glass, where you see there is there is a bonding, there is a equivalent bondings are there, but the pattern is not periodic. So this is that is why the glass is not. Then why it is short range? If you see very clearly, this is silica. Here also this is silica. This is oxygen. 3 oxygen is always associated with 1 silica. Is shared. We have the shared oxygen, right? So if you see this silica tetrahedra, this silica tetrahedra with the shared oxygen, they have a particular structure which is still existent in the glass, but the long range periodicity is not there, but the short range periodicity, that's it. It's called short range order. And this is another sodium silicate glass where sodium has been incorporated inside the glass. So what will happen? They will again bond. Still up to this quartz glass, we have the amorphous nature, but they are all bonded with one another. So oxygen in between two silica is called bridging oxygen. Now, when we put sodium, there will be non-bridging oxygen starting coming out, and that hugely alter the properties and of this glass. So we'll slowly come to this in the some of the few slides. And this is a basic accepted this thing silica tetrahedra model. So all at the center will be now silicon ion, and there will be shared oxygen here, and it forms a tetrahedral form, and that basic unit will be repeated everywhere. So whenever you see a glass structure, you will see this kind of structure again. So this is a three-dimensional picture. If you see again, in a crystalline pattern, you have again these tetrahedrals forming a periodic atomic structure in the long range periodic atomic structure is there. But when it comes to glass, the tetrahedra is there. The tetrahedra form is there, which is short range, but you don't have a long range periodicity. So that's where the difference is coming. So that's why this is again here is another more complicated sodium, calcium. You can incorporate many, like that radiation shielding, radiation waste management also. You can incorporate this barium and other this radioactive products inside the glass matrix, so that they will not come out easily. So that's how the glass structure is so stable. And okay, now slowly moving on to the glass transformation temperature now. It's very important. You have to understand this glass transition temperature. This is the main two things, the amorphous nature and the glass transition for the glass. This is very unique for the crystals don't have this glass transformation temperature. So this is typically a glass blower pouring some liquid glass in a sand casting. This is called sand casting. You have sand molds, and you put the molten liquid here, and slowly when it cools down, you will see the glass like this kind of thing coming out. And that is how we have this very this thing coming out. The glass is cooled. Now what will happen, look at the picture here. This is the enthalpy of volume versus temperature, and when you're cooling, this is the temperature increase decrease. So when you're starting from this temperature, little higher temperature, like the temperature here. Now what will happen when you are cooling down, if it is a crystalline nature, what will happen, it will drastically drop at this point, and then we have this exothermic reaction here, and we form this crystalline structure here. But if you supercool it, if you fast quench, because of the fast quenching, you don't allow the silica to rearrange themselves. So what will happen, that's what's called melt quenching. This is, you are quenching it very fast. So it will happen that if you go through a super cool liquid, it will bypass the melting point, and then it will gradually goes here. Still up to this point, this is liquidic nature. They are liquid-like nature, but after certain time, what will happen, the mobility of the ions and the atoms will be stopped, because it will be frozen. And so it is, and gradually it become a solid glass. Yeah, at this point it's a glass, it's a crystal, it's a glass. The volume is higher compared to the crystals, so that's why the density is less for the crystals, for the glasses. And so this is what is called the glass transformation temperature. There is from liquid to solid, there is a point where there is a kinetic arrest of all the movement of the liquid. So the structure is more like a liquid, but it's a solid. This is the beauty of glass, and you can use this for many other applications. But main application is the glass blowing, and I will say this is again the stiffness of the glass compared to the temperature. You can measure it, and so initially the stiffness is very high in the glass, is solid glass state. Now at certain temperature, the stiffness starts going down, and become a rubbery state, rubber-like state, elastic. So then it starts flow, and then it will become a viscous flow. It's molten here. So generally working temperature is beyond glass transition temperature. This is a temperature, a fictive temperature. It's called the glass transition temperature, but we have to work beyond that for having some kind of deformation in the glass. So again, the viscosity has been plotted against the temperature. If you see, viscosity decreases with the increase in temperature. So whenever you have a glass, we have to cross the strain point, annealing point, glass transition temperature, softening point, and this is a working point around 1000°. This soldering glasses, we have the 1000° Celsius is a working point where you can actually work on the glass and you can blow this also, the glass blowing technique. See, this is a glass blowing, a typical glass blower, and this is the person, what he's doing is he's putting some gas through it. It's like a balloon. It's blowing up like a balloon, as you can see. It's like a balloon. It's blowing up. Some people are showing to some demonstration here. So it's a very hot glass, but at this temperature only you have to blow it. So it will blow up like a balloon, and you can give us very beautiful shapes and size of it, and that is what is called glass blowing. Now I'm moving on to the more specific this analysis techniques. These are very specific analysis techniques we have in our lab. This is one of the most important things is a differential thermal analysis, where we can exactly find out when we make some glass, we have to find out what's the thermal characteristic of it, like what is the specific heat of the glass, what is the glass transition temperature, and what is the crystallizing temperature and all. We can find it from this DTA curve. So this is a DTA instrument, DTA instrument. But at the base of this, we have a furnace. It's very small furnace is there, and there are two crucibles. One will be reference, one will be sample. Now, what we do, we have to measure the temperature difference between these two crucibles. That is what is differential thermal. So if there is a exothermic reaction or endothermic reaction, that will be shown here. As you can see here, that there is a heat flow versus this temperature, where if there is a peak coming on this side is exothermic and this side is endothermic. So this is a typical curve for a glass, where this is the glass transition temperature, and then it goes some crystallizing temperature at this point, and then it goes to melting temperature. It's very, very important technique, very important information we get from thermal analysis. Another very very important parameter is the coefficient of thermal expansion. This is also again related to furnace. What will happen? We have to put the sample into the furnace, and then we will put a probe on top of the furnace sample. Then that probe will be attached to a detector and forced upon that to give some kind of stability, and then we'll increase the temperature. What will happen? See the picture in the right hand side. This is the potential energy versus distance curve. So it's very common. I think you can see it in your textbook also. This is the average distance, this potential curve, and the average distance of the average interatomic distance increases with the temperature C. So if the interatomic distance between the molecules increase, there will be an increase in the length in the volume of the sample. That's what we have to measure using this technique. So delta L by L will be is equal to alpha delta T. Alpha is the coefficient of thermal expansion. So finding the coefficient of thermal expansion of this glass also of any glass is important, because if you remember, I've talked about this glass to metal seals, where for making this electrical feed throughs, we need to match the thermal expansion with a metal. So that is very important parameter. Now density also is very important, and density varies. That's what I was saying. Density varies a lot with the composition. See, simple mole percent 10, 20, 30, 40 with the alkaline oxide, the density can vary from such a huge range. So that's how the density is measured is mass per unit volume. It's the same old Archimedes principle. So you measure the mass in the air. This is the balance, what we the electronic balance we have. So measure the mass of the sample in the air, then you put it in water or any known density liquid. So what will happen again? Using Archimedes principle, we can find out the density. So basically, the weight of the displaced liquid will be equivalent to the loss in the weight. So that's how we measure the density. Now hardness, how we measure here. This is also very important parameter. We have generally hardness is we need a harder material. This is a specimen what we have. Suppose we have a glass specimen here, and then you put a diamond indenter. We have a diamond indenter with a test load. So we give some kind of force to put the diamond load inside the sample in a hardness measurement machine. So what will happen, because the hardness of the diamond is more than the glass, most of the glasses, and so that will go inside and make an indent and make us impression, like as you see here in the right hand side. It makes an impression, 3D impression. It's a impression is been made by the diamond tip. So depending on the length of the indent, we can measure what is the hardness. So this is what it has been measured. So this is a 20 micron length of this thing, and hardness 539 measured. So this is how we measure the hardness. Then refractive index is being measured by a shadow boundary. Is also very important parameter for measure of a glass, especially the optical glasses. Then refractive index is very important. Well, this is a very simple technique. We have a prism here. Look at the picture at the left. We have a prism here. We have a light source, and we have a screen here. So you will see there is a shadow boundary here, and this is because the total internal reflection. At a certain point, the light will start bending back towards it, and that depends on the refractive index of this material, of the test material. So that is how we can measure the shadow boundary. And from shadow boundary, this is actually how this is the instrument we have. This is a Atago instrument which is having a this digital refractive index measurement. But what we see here, we have to choose the crosshair at the particular point. So because of the this point, we can measure what is the refractive index of the particular glass, particular wavelength of light. And from there, we can measure the dispersion also if we change the filter of the glass, filter of the light source. Now, I'm coming again a little bit diversion to this electromagnetic spectrum, and I will show some of the interaction with the material. So electromagnetic spectrum, as we all know, we were more habituated with this. They are interconvertible with E is equal to hc by nu, h nu, hc by lambda. So wavelength, lambda, frequency, and photon energy can all be actually interconvertible. But mostly in the spectrometry, we take the wavelength as a measuring parameter. So in the electromagnetic spectrum, the visible light is very small part of the electromagnetic spectrum. As you can see, we have only a very small part, as you can see, but it varies from gamma rays, X-rays, ultraviolet rays, visible light, infrareds, radar, microwaves, television waves, radio waves, and all this part of the electromagnetic wave. And they react very differently with the material. So some of them I will discuss here. And first of all, the transmission. This is also interaction of the light. So if you have basically this is a spectrometer, but I will show here how the transmittance is actually happening. So we have a light source, and we have a sample, glass sample. So light is going through the sample, but in the process, it can get reflected, it can get absorbed, and also it can get scattered also, so to some extent. But most of the glasses don't have, but there is a part where it can scattered. So, and then the rest will be transmitted. So this is a typical transmission spectra of a float glass from the Scott, another very big European company, Scott Glass. And this is the transmission of a 2 mm thick float glass, where the transmission is almost 90% of the visible region. See, this is 400 to 700. This much is only the visible range, and beyond that, if we have the spectrum visible transmission beyond that also. But again, there is a sharp drop to 0%. There is no transmission at this wavelength, maybe some ultraviolet position and some IR position. So there are some absorption beyond this position. This is called the absorption age in the UV range. This is absorption in the IR. So we'll come to that also a little bit in the next slide. So absorption, why absorption is happening here. So basically glass, if we know this is there's a electrical not conducting, and this band gap is very large, right, compared to the metal or a semiconductor. So band gap is very big. So there is a valence band and the conduction band, and in between this is band gap. So what will happen when the light of enough energy like UV light, which is up to the energy compared with the band gap, that light will be absorbed by some of the valence electron, and it will be kind of coming back to the be excited to the conduction band. So that's how there is an UV absorption age in the transmission we have seen earlier. This is UV absorption age, or sometimes called electronic absorption age, and another is IR absorption age, which is because of the molecular absorption. See, these are the modes of the molecular absorption, where we have this. Suppose we have this water, very simple water molecule. They have three different this symmetric stretching, anti-symmetric stretching, and bending vibrations. So they again absorb some of the IR light coming on the way. So that way they are absorbing. And that is similar. There is the symmetric, asymmetric stretching, bending modes there for silica, and that's how we get the molecular absorption, and that can be measured by this Raman spectroscopy. C.V. Raman, our very famous Indian scientist, and he has actually designed this kind of experiment, and he was the first person to make this Raman spectroscopy and find out some of the different colors coming out in the waters, like Mediterranean region and all. The water is very green, and he explained because of this Raman spectroscopy and molecular absorption of the light. So anyway, so this is again is happening in the glass also. He has worked some with the optical glasses also. Anyway, the fluorescence spectroscopy, this is getting a little tougher, but I have not much left. On the 46 slide is going on. So fluorescence spectroscopy is again another way of interaction of the light with the matter. So obviously in the matter there is an electron which is lying mostly in the lower level. As you see here in the pumping or excitation, what will happen? The electron was lying in this lower energy level, but when you get some energy which is equivalent to the energy difference between these two levels, what will happen? It will be excited to the upper energy level. This process is called pumping or excitation. So we'll pump the electron from the lower energy level to excited level, and then what will happen? After a certain time, this electron in the upper energy level will come down to the ground state again, and that is when again that will release some photon, and that is what is called spontaneous emission. But this is of noise. That will go in any direction and all. So this is spontaneous emission. But what will happen when we have another photon coming, and there is a photon induced relaxation? What will happen? One photon is coming, and that will induce the electron. That will induce the electron from the higher energy level to come down to the ground state, and then these two photons will act like in a twin twins. They are almost identical. So that's what is called stimulated emission. So you have this photon has stimulated another emission, and they are very much identical. That's how the basic laser will be generated in a cavity. So they are having, so this is what is called stimulated emission, and we can measure it in the fluorescent spectroscopy. Now, laser matter interaction. Laser, what we have earlier shown, this laser had very high interaction capacity, like engraving. In the left, you have seen this is a wooden piece, and using a laser, you can make very intricate patterns inside the wood or in the metals or in the leather. You can make very, even portraits we can make in this. You can make in this thing. So basically, what will happen? The laser, when you are concentrated, they have certain energy which will burn the wood at some part, and they will form this kind of geometry. And what will happen in the glass? This is what is shown in the glass. So in the, when you put the laser in with the glass, there's also, it's not burning, but it's melting. But when it resolidifies, it is forming some kind of structure, and that's how we can make different structural patterns, like I've seen here. And because it is transparent, you can make the pattern inside. This is the Eiffel Tower. Famous Eiffel Tower has been made inside the glass block. So this is how the glass can be used for engraving, and very different kind of interaction. There are interaction of laser with the glass to make some optical waveguides and all. So that is also in the process. Now, high energy photons, which is mostly the gamma photons, are very high energy photons. They are also interact in very different manner when it goes to a glass or any metal like copper. So this is what is happening here. This is the gamma energy shown here with the interaction probability. And what we have seen, that there is a initial part where there is a photoelectric effect, and then there will be Crompton effect, and then there will be for electron positron pair productions. So yeah, photoelectric effect, as you see, is a photon is absorbed and electron expelled from the atom. Now, Crompton effect is that there is an inelastic scattering of the gamma photon with an atomic electron, and this electron positron pair, that is produced only when the gamma energy is above 1.02 MeV. This is the minimum energy required to create two particles, because the rest mass of electron is according to that. That's how it comes. So this is how the gamma photons are interacting with the glass, and you see this is how it really actually makes. This is a radiation induced color centers formed in the glass. See, this is a glass block there initially. Then when you put it in the radiation zone, if you put it in the radiation, what will become brown like this? And that's because what will happen, see in the left, there is a radiation coming and will knock out some of those electrons from the orbit, and that is why it is called ionizing radiations, right? So, and that electron hole pairs will generate some kind of energy levels in between the conduction and the valence band, and that forms a this particular color, brown color. But that will again go, you can remove that with time, and also with putting some temperature on this glass without deforming anything. Actually, you can get back this glass again maybe around 300 or 400 degrees Celsius temperature. And finally, this electron matter interaction. This is very big. This thing, electron are used for SEM, TEM. These are very useful techniques, very useful, very often used in the laboratories, the SEM and TEM. And this is the SEM picture of one of my optical fibers I have made in the University of Bath. And this is what is showing. See, this is 10 micron. So you can understand how thin this air bubbles are running through the fibers. Now, how they interact, mostly when a primary electron beam goes into the sample surface, what will happen? There is secondary electrons coming out from there. There will be backscattered electrons coming out here. There will be Auger electrons coming out here, and there will be characteristic X-rays coming out from this volume of primary excitation. So this area is generally 1 to 3 micrometer depth, and you can get. And now, if you scan at every point of this thing, you can get a very good picture of this, and the depth of focus is very high for this kind of microscope, which is much better than optical microscope. Optical microscope, we see the field view, but here we are scanning, so that's why the depth of focus is very high. So I will summarize now. We are almost at the end. This is initially I have started talking about the history of the glasses, and gradually the utilities of glasses and the properties I have mentioned, like the float glass, and then I have the optical fiber glasses. I've talked about the different other applications like special glasses and nuclear industries. Then fabrication techniques of the laboratory glasses, I have this melt quenching techniques, the uses of furnace, the annealing, and definition of glasses I've talked about. Hopefully you have understood the amorphous structure and glass strength, and these are two main parameters we have to understand for this for the definition of glass, and the characterization techniques or the testing techniques like optical, thermomechanical, and structural properties of the glass. So with this, I end my lecture, and I thank you all for your kind attention. And yeah, thanks.
Thank you, Dr. Nandi. Hello, am I audible?
Yeah.
Thank you, Dr. Nandi, for your kind presentation.
Yeah.
Now I requesting all the participants, if you have any question or queries, please write it in the chat box.
Yeah, please don't.
Please write it in the chat box if you have any questions. One question is there.
Okay.
Hello. By Dr. Onimes Laik.
Where is it? If you could someone read it. Is there any easy homemade experiment apart from gravity measurement that we can differentiate between glass made from artificial gem and natural gem? Say artificial gem and natural gem. I don't know. I mean, if it is a crystal, if it's a glass and crystal, if you simply put it in the this thing, X-ray, or some Raman experiment nowadays are very handy for differentiating. But I have seen one when I was in somewhere in near this thing. Say there are plastics they are trying to sell as this shells, like the beautiful pearls. They are trying to sell the plastics. So the one basic technique I will say, you just put some fire, like lighter, put it in lighter. If it is not a real one, it will burn off. And so that is how we can. Another is crystalline characteristic of glass increases over the amorphous characteristics with the age of the glass. There is a possibility, but that age is millions of years. There is obviously a possibility, but it's a million. But you can promote that with that thermal this thing. If you heat it, there's one experiment I have shown, that differential thermal experiment. So at one point, if you put it in a furnace, at some glasses will easily form crystalline structures, and that's how the Macor, that machinable glass ceramics, that is actually crystalline, partially crystalline. It's a crystals embedded inside the glass matrix. So that's how you can do some kind of crystalline. You can grow the crystalline nature inside the glass. Yeah.
Hello.
So
Onimes Laik asked, can we ever predict the broken pattern of any glass? Can you ever predict the broken pattern of any glass? How does it control?
Prediction. Okay, prediction is very
broken
difficult.
Pattern.
Prediction is very difficult, but obviously prediction means you want to make some kind of computer calculations. For glass, it's very difficult because of this amorphous nature. Actually, it's very difficult to predict which way this thing will go. But obviously, it's very general pattern you can predict depending on the stress. If you have to do the stress calculation, you have to do the stress measurements, or maybe some hardness measurements and all. But still, it's difficult. It's difficult, I would say. Yeah, it's difficult.
Hello.
Huh.
I think
Okay.
there is no more questions.
Yeah.
So I requesting Dr. Onimesh Das, please, sir. Sir. Hello.
Hello.
Yes, sir, please.
Hello.
Hello.
Yes, sir, bolun.
Okay. We have now reached to the concluding part of the seminar. Now it is the time for vote of thanks. We express our thanks and gratitude to Dr. Purnananda Nandi for his lucid and informative presentation. Use of glass in laboratory and in domestic life as decorative material to prepare showpieces is now known to all of us. Our speaker has highlighted the most important use of glass in nuclear industry in his speech. We are thankful to our teacher in charge, Professor Debashish Rai Choudhury, for his support and encouragement. It will be injustice if I do not recognize the sincere effort of the head of the department, Dr. Rima Pal, and the convener, Dr. Biplab Goswami, in organizing the seminar. We are also thankful to Mr. Tushar Kundu, along with Mr. Sujan Saha and Subhankar Barman for the technical support. Lastly, but not the least, we are thankful to all of our colleagues and the participants who have shared their times with us to make the seminar a success. Hope we will meet again in this platform. Stay safe and well. Thank you all once again. With this, I declare the seminar end.
Hello. Hello.
Hello.
Sir, feedback link and certificate এই সম্বন্ধে একটু বলে দিন তাহলে। Hello.
Hello.
Feedback.
Here is an announcement. All the participants are requested to submit their feedback in the feedback link provided in the chat box.
And certificate will be given within 5 days of the seminar.
Okay.
Hello. Okay. So now it is.
Okay. Thank you.
Thank you.
স্যার আমি লাইভ অফ করে দিয়েছি। ওকে স্যার।